Welcome to the Space Sleeper. Tonight, we're drifting into dreams with a calm, quiet journey to one of space's strangest places, the heart of a collapsed star. These are neutron stars, the dense, bizarre, and quietly powerful leftovers of brilliant giants. They're tiny, heavy, and mysterious, bending time and space around them. Wherever you are tucked in bed, on the couch, or just between thoughts, I hope this helps you relax. If it doesn't lull you to sleep, at least you'll learn some astrophysics. If you're enjoying this cosmic bedtime story, a gentle like and a subscription would be wonderful so you don't miss the next one. Let me know in the comments where you're watching from and what time it is. Now, breathe slowly, get comfortable. The stars have exploded, but all is calm. Disclaimer: this video is for educational and relaxation purposes only. It is not medical advice. Consult a professional for health concerns, including excessive fascination with neutron stars. The birth of a neutron star. From cloud to collapse. Long before a neutron star exists, there's a sprawling nursery of gas, dust, and the remnants of other dead stars. These are stellar nurseries. Here, gravity starts its slow, busy work. Particles in a cloud gradually gather, pulling each other closer. More mass means more gravity, creating a feedback loop that eventually forms a glowing core. This core becomes hot and dense enough to ignite nuclear fusion, the magic that turns dust into a baby star. Hydrogen atoms smash together to form helium, releasing energy that pushes outward, balancing gravity's inward pull. Not all stars are equal. Small, red dwarfs simmer for trillions of years. Our sun lives a moderate life, about 10 billion years of stable warmth. Then there are the giants, the future parents of neutron stars. These massive stars live fast, burn hot, and die young. To become a neutron star, a star must start with at least 8 times the mass of our sun. Some are dozens of times more massive. These stellar heavyweights burn through their fuel quickly, fusing hydrogen into helium, then carbon, oxygen, and so on, creating heavier elements. Each stage burns faster than the last, lasting only years, months, or even days in the star's final moments. Then they hit the iron wall. Unlike lighter elements, fusing iron consumes energy. The fusion engine stalls. With no outward pressure, gravity takes over, and the star begins to fall inward. These massive stars are cosmic forges. The carbon in your DNA, the calcium in your bones, the oxygen you breathe, almost everything you're made of was born inside a star like this billions of years ago. Stars don't just light up the universe, they build it, often ending their lives dramatically, sculpting interstellar space, and sometimes forming binary systems. The supernova, a grand finale. The core's collapse is astonishingly fast, less than a second. Temperatures soar to over 100 billion degrees. Electrons are forced into protons, creating neutrons and neutrinos, a process called neutronization. The core becomes a dense soup of neutrons, while neutrinos, nearly massless and ghostly, flood out in all directions. Imagine a bowling ball collapsing into a marble in a blink. That's the scale of compression. The core, once thousands of kilometers across, shrinks to only about 20 kilometers wide. The star's outer layers, unsupported by fusion, crash inward at a significant fraction of light speed. When this material hits the incompressible neutron core, it rebounds violently. This rebound, combined with a neutrino rush, creates a shock wave that blasts the outer layers into space in a supernova, one of the most energetic events in the universe. A supernova is absurdly bright. For a brief period, a single exploding star can outshine an entire galaxy, hundreds of billions of stars. The energy released in a few seconds is more than our sun will emit in its entire lifetime. To an outside observer, it looks like a sudden brightening followed by a slow fade over weeks or months. Inside, it's chaos. Elements forged in the star's core, carbon, oxygen, calcium, iron, are flung into the cosmos, becoming the raw material for new stars, planets, and even life. Every atom of iron in your blood came from a supernova. If the collapsing core is massive enough, at least 8 times the mass of our sun, but not too massive for a black hole, it survives the blast. The pressure from packed neutrons halts the collapse, forming a neutron star. This newborn neutron star is incredibly hot, over 100 billion degrees, spins rapidly, often several times per second, and its magnetic field intensifies. The gentle glow of a living star is replaced by a dense, spinning magnetic corpse, packed tighter than anything else in the universe short of a black hole. Stars are the universe's great recyclers. They spend their lives resisting gravity, only to be undone by it in the end, lighting up the universe with a brilliance that echoes across space and time. It's peaceful, poetic. A star collapses, and something new is born. Not quite alive, not quite dead, just different, quiet, dense, mysterious. The twinkling points in the night sky include these calm survivors of ancient chaos, holding secrets heavier than anything on Earth, all from a simple cloud of dust. The neutron star, a cosmic oddity. A neutron star is small, only about 20 kilometers across, the length of a leisurely morning drive, but incredibly dense. It's the heavyweight champion of the universe, short of black holes. Matter here is crushed so tightly that atoms no longer resemble anything we know. If physics had a basement, neutron stars would live there. Imagine taking a teaspoon of neutron star matter. That single spoonful would weigh about 6 billion tons, roughly the mass of Mount Everest crammed into something small enough to stir your tea. This matter would slice straight through Earth. Let's explore its layers. Atmosphere. A few centimeters thick, it's a paper-thin layer of exotic plasma where light and matter blur. Light trying to escape is gravitationally redshifted, appearing redder and less energetic. Outer crust. An ultra-dense layer of crystalline nuclei packed like sardines, surrounded by a sea of free electrons. If you dropped a marble from waist height, it would hit the surface at several thousand kilometers, vaporizing it. Inner crust. Pressure forces electrons into protons, creating neutrons. These neutrons drip out, forming a neutron-rich soup coexisting with nuclear clusters. Scientists call this the neutron drip region. Pasta layer. In this weird region, atomic nuclei arrange into rods, sheets, and blobs nicknamed spaghetti, lasagna, gnocchi, and even Swiss cheese. This is nuclear matter denser than anything on Earth, and it might be the strongest material known to science, over 10 billion times stronger than steel. Outer core, believed to be a superfluid of neutrons, meaning neutrons flow without frictiona liquid that never slows down or splashes. It might also contain superconducting protons and electrons. Inner core. Here, things are speculative. Theories suggest neutrons break down into their constituent quarks, forming a soup of quark matter, up, down, and possibly strange quarks. This hypothetical substance, perhaps an ultraloidic state, might exist nowhere else in the universe. Other theories suggest hyperons, particles similar to neutrons but with additional quarks, or other exotic particles. We don't know for sure what's at the very center. No Earth lab can replicate these conditions. One thing we do know: neutron stars spin fast. Due to the conservation of angular momentum, a star that once rotated every few days can now spin dozens or even hundreds of times per second. These rapidly spinning neutron stars are called pulsars. They also have colossal magnetic fields. A typical neutron star's magnetic field is trillions of times stronger than Earth's. Some, known as magnetars, have fields over a quadrillion times stronger than Earth's, a 1 followed by 15 zeros. Such a field could strip information from a credit card from halfway to the moon. Despite this insane density, crushing gravity, and magnetic fury packed into a city-sized sphere, neutron stars are among the most stable objects in the cosmos, persisting for billions of years. They are like cosmic fossils, frozen in a state of extreme physics. We're still peering through a cosmic keyhole, wondering what's on the other side. Existence near a neutron star. Warped reality. Standing on a neutron star's surface isn't advisable. Physics itself becomes uncooperative. Gravity. On the surface, gravity is intense, over 200 billion times stronger than Earth's. If you weighed 70 kilograms, you'd weigh about 14 quadrillion kilograms. Escape velocity. Earth's escape velocity is about 11 kms. On a neutron star, it's around 150 kilometers, more than half the speed of light. Launching a rocket would require planetary-sized fuel tanks. Gravitational redshift. Light escaping the star loses energy and shifts to the red end of the spectrum. The star isn't changing color. Space-time is. Time dilation. Time itself moves slower near a neutron star. A minute for you might be several minutes for someone far away. A few years near the star could mean decades pass elsewhere. It's not quite time travel, but it's close. Gravitational lensing. Intense gravity curves space so dramatically that objects behind the star can be seen around its edges, making the tiny neutron star appear much larger, like a cosmic magnifying glass. These distortions make neutron stars incredibly useful for scientists to test gravity theories and probe matter under extreme conditions. Imagine floating a few kilometers above a neutron star in a special pod. It looks like a perfectly spherical orb, about 20 kilometers wide, smooth, rigid, and unimaginably dense, like brushed metal. It's incredibly hot, over 1,000,000 degrees Kelvin. The horizon curves sharply upward due to gravitational lensing, letting you see more than half the surface. Your clock runs slowly compared to Earth time. A few hours for you could be days back home. Magnetic fields swirl with unimaginable strength. If it's a magnetar, the field could be quadrillions of times stronger than Earth's, strong enough to distort atoms. Occasionally, the neutron star might glitch, a sudden, tiny speed-up in its spin, caused by a starquake, a shift in its rigid crust, or interactions with its superfluid interior. It's like a cosmic hiccup, a blip in the universe's rhythm. Then the spin continues, and the pulses resume. You pull away, and the star shrinks to a speck, still pulsing, still whispering. Your clocks resynchronize with Earth time. You've witnessed a place where physics is pushed to its limits, reminding you that even tiny points of light can hide the deepest wells of gravity. Pulsars, lighthouses of the universe. When massive stars collapse into neutron stars, they don't just shrink, they spin faster due to the conservation of angular momentum. A star that once rotated every few days can now spin dozens or even hundreds of times per second. This spin is incredibly stable. Some pulsars keep time better than atomic clocks, with precision measured in microseconds over years. Not every neutron star is a pulsar. It needs a strong magnetic field and a decent spin. The combination rips charged particles from the surface, accelerating them along magnetic poles, emitting beams of electromagnetic radiation, usually radio waves, but also X-rays or gamma rays. Because the magnetic axis is usually misaligned with the rotation axis, these beams sweep through space like a lighthouse, creating regular pulses if they cross Earth. The first pulsar was discovered in the late 1960s by Jocelyn Bell Burnell, a graduate student. It pulsed every 1.3 seconds. Initially joked as LG Moan, Little Green Men, its true nature was soon revealed. Millisecond pulsars spin hundreds of times per second, the fastest known at over 700 times per second. These are thought to be recycled pulsars, sped up by stealing matter from companion stars' cosmic vampires with eerie elegance. Pulsars are surprisingly useful. Astronomers use them as natural cosmic clocks to detect tiny wobbles from orbiting planets or the stretching of space-time due to gravitational waves. There's even talk of using them for spacecraft navigation. Binary pulsars, like the famous Hulse-Taylor binary pulsar, provided the first indirect evidence for gravitational waves as their orbits slowly spiraled inward, exactly as predicted by Einstein. Pulsar glitches sudden, slight speed-ups are thought to be caused by starquakes or interactions within the superfluid interior. They offer a rare window into the deep interiors of neutron stars, like watching a cracked bell to learn about its metal. Rare anti-glitches, slowdowns, also occur, reminding us of their surprises. Pulsars are absurd city-sized spheres of degenerate matter, radiating energy through immense magnetic fields, yet from Earth they are steady, soothing beacons, like metronomes in the vast silence of space. They remind us of reliable patterns amidst galactic chaos, making them perfect bedtime companions, gently persistent, ticking, beating, flickering. Magnetars, magnetic titans. Some neutron stars take their extreme properties even further, becoming magnetars, neutron stars with magnetic fields so powerful they make ordinary ones look like fridge magnets. A typical neutron star's magnetic field is trillions of times stronger than Earth's, but magnetars' fields can be, over 0 times stronger than that. Around 1 quadrillion Gauss, 1 followed by 15 zeros. This field is so strong it could erase a credit card from a distance equal to the moon. It even affects the vacuum of space, making it birefringent bending light differently, a phenomenon confirmed by astronomers. Magnetars are thought to form from especially massive stars with rapid spin and high internal magnetic fields during collapse, compressing and amplifying the field to monstrous levels. Interestingly, magnetars don't spin fast for long. Their intense magnetic fields create drag forces that quickly slow their rotation. Most spin only once every few seconds. They are known for outbursts, sudden intense flares of X-rays and gamma rays that can release more energy in a single second than the sun emits in 100 years. Some are detected across the entire galaxy. The most powerful recorded flare on December 27, 2004, from 50 light-years away, was briefly the brightest thing in the sky. These outbursts are believed to be caused by starquakes, sudden cracking of the neutron star's rigid crust under immense magnetic strain. Magnetar flares are scientifically useful, acting as natural laboratories for high-energy physics. Despite their fury, magnetars have relatively short and quiet lives. After about 0 years, a blink in cosmic terms, their magnetic fields weaken, and they fade into ordinary neutron stars. Only a few dozen confirmed magnetars exist. Fast radio bursts, FROBs, might also be linked to magnetar activity. Magnetars are powerful and dangerous, but also surprisingly fragile. They arrive with a bang, spin down with a sigh, and vanish like cosmic ghosts. But in their brief lives, they show us the raw power of the universe. They are masterpieces, strange, brief, and unforgettable. Glitches, the star's hiccups. Neutron stars appear still from a distance, with steady pulses and elegant spins, but internally they're anything but calm. Deep within these cosmic pressure cookers, something shifts, causing the star to twitch, a sudden, momentary hiccup in the universe's rhythm called a glitch. Pulsars are famously reliable, some rotating hundreds of times per second with such consistency that astronomers use them as cosmic clocks, with differences measured in microseconds over years. Yet, occasionally, the pulse speeds up slightly, a few parts in a million. This contradicts the expected slowdown from friction and drag. Pulsar glitches were first discovered in the late 1960s with the Vela pulsar, a young neutron star about 10 light-years away. Possible causes: starquakes. The ultra-dense, billions of times stronger crust suddenly shifts, cracking or rearranging. This shifts mass closer to the rotation axis, causing the star to speed up like a spinning ice skater pulling in their arms. Superfluid vortex unpinning. Beneath the crust is a superfluid of neutrons that flows without resistance, forming tiny whirlpools, quantized vortices. These vortices can get pinned to the crust. As the outer crust slows down, tension builds until the vortices unpin all at once, transferring angular momentum to the crust and speeding up the star. Both models likely play roles. Glitches are a rare window into neutron star interiors, revealing clues about crust strength, superfluid behavior, and magnetic field configuration. After a glitch, the spin rate slowly relaxes back to its pre-glitch rate over days, weeks, or months, as if the star remembers its original rhythm. Sometimes, glitches are accompanied by changes in the pulse profile, suggesting magnetic field shifts or subtle stellar rearrangements. There's something poetic about a star, a dense remnant of something long dead, still capable of shifting, quaking, and changing, a living machine full of tension and movement. Even rarer are anti-glitches, where the neutron star suddenly slows down. These unpredictable events remind us that neutron stars are full of surprises. They creak, twitch, remember, and adjust, whispering through the vacuum of space. How we study the invisible, cosmic fingerprints. Neutron stars are invisible by nature's mall, dense and dark. Yet, we've learned a great deal by studying their many fingerprints on the universe: radio waves, X-rays, gamma rays, and gravitational waves. Radio telescopes. This is how pulsars were first discovered in the 1960s, regular clock-like signals from spinning neutron stars emitting radio beams. By timing these pulses, scientists determine rotation rates, slowdowns, and orbits, even detecting tiny wobbles. Radio observations also map the star's magnetosphere. X-ray and gamma-ray telescopes, space-based telescopes like NASA's Chandra or ESA's XMM, Newton observed neutron stars emitting bursts, flares, and streams of X-rays. Many emissions come from accreting neutron stars, pulling matter from companion stars, heating it to millions of degrees. X-rays also study magnetar outbursts. Gamma rays, the most energetic photons, are detected by telescopes like Fermi, revealing how particles accelerate in fierce environments. Gravitational wave astronomy. In 2015, gravitational waves, ripples in spacetime, predicted by Einstein, were first directly detected from colliding black holes. In 2017, a historic signal, 170,817, came from two neutron stars spiraling together and colliding about 130 million light-years away. Seconds later, a burst of gamma rays and visible light were detected. This was the first time a cosmic event was observed with both light and gravitational waves, marking the dawn of multi-messenger astronomy. We learned that these collisions produce kilonovae, bright explosions that forge heavy elements like gold and platinum. Fast radio bursts, FRBs. These mysterious, extremely brief pulses of radio waves from distant galaxies are now linked to neutron stars. One repeating FRB was traced to a known magnetar. Neutrinos. Neutron stars produce vast numbers of neutrinos during supernova formation. Though difficult to detect, trillions pass through your body every second. Future observatories might reveal the inner workings of stellar death. It's incredible that we, tiny creatures on a rocky planet, can study the remains of dead stars thousands or millions of light-years away using sophisticated instruments. Neutron stars don't show themselves easily, but when we tune in, we find they've been speaking to us all along in pulses, flickers, and the stretch and squeeze of space-time itself. Mergers, cosmic forges, and gravitational waves. Neutron stars spend most of their lives alone, but sometimes they find a partner, another neutron star or a massive star. When their orbits shrink over millions or billions of years due to gravitational wave emission, their dance quickens until they merge. The collision of two neutron stars unleashes a flash of gamma rays, a shower of gravitational waves, and a glowing radioactive explosion called a kilonova. Kilonovae are a special kind of supernova, shining 1,000 times brighter than a typical nova. Most importantly, kilonovae are factories for the heaviest elements in the universe: gold, platinum, uranium. These elements require extreme conditions and rapid neutron capture, exactly what a neutron star collision provides. Chunks of ultra-dense, neutron-rich matter are ejected, undergoing R-process nucleosynthesis to build up heavier elements in seconds. The 2017 detection of 170,817 provided the smoking gun, direct proof that neutron star mergers create these heavy elements. This multi-messenger astronomy event, gravitational waves, gamma rays, visible light, X-rays, radio waves, showed that these collisions are vital to the cosmic economy, providing ingredients for worlds and everything on them. If you wear gold or have platinum in electronics, it may have been forged in such a merger billions of years ago. Neutron star black hole mergers can also occur, sometimes tearing the neutron star apart to create a kilonova. Some theorists even believe that two merging neutron stars may briefly form a hypermassive neutron star, an object so dense it collapses into a black hole in a fraction of a second, emitting complex gravitational waves. These events are rare, perhaps only once every 10, 0 to 100, 0 years in our galaxy, but spectacular, bright, and full of meaning. They prove that even in death, stars give, and even in collision, the universe creates beauty in the form of precious metals, new elements, and glowing clouds of light. The heart of mystery, exotic matter. Even after all we've covered, we've only scratched the surface of neutron stars. At their core, they may hide some of the strangest, most speculative forms of matter. You know, neutron stars are mostly made of neutrons. But when matter is compressed to several times beyond the density of a normal atomic nucleus, neutrons themselves might break down into their fundamental components, quarks. Quark matter. Protons and neutrons are made of quarks, up and down quarks. In a neutron star's core, conditions might be so dense that neutrons dissolve, releasing their quarks into a sea of quark matter, or quark-gluon plasma, a substance that may have existed in the first microseconds after the Big Bang. This could be a dense, frictionless fluid of up, down, and possibly strange quarks. Strange quark matter. Some physicists believe this might be more stable than ordinary nuclear matter, leading to the terrifying but unproven theory of stranglets, droplets of strange matter that could convert ordinary matter into more strange matter, like a subatomic zombie infection. Hyperons? Other exotic particles like hyperons, neutrons with additional quarks, such as a strange quark, might also lurk in the core. The composition of the core determines how the star behaves. Quark stars, hypothetical stars made entirely of quark matter, might even be a separate class of objects, smaller and denser than neutron stars. Detecting them is tricky, but subtle differences in their cooling or collision behavior could reveal their true identity. Even more speculative ideas involve dark matter accumulating inside neutron stars, altering their behavior or triggering collapse, or the existence of Bose-Einstein condensates and other exotic forms of matter. Neutron stars are playgrounds for every weird theory physics has ever invented, sitting at the crossroads of gravity, quantum mechanics, particle physics, and nuclear science. We're on the verge of finding out more. New observatories like NICER are measuring neutron stars with unprecedented precision to determine their exact size and mass, helping to pin down the equation of state, the relationship between pressure and density, and reveal what kind of matter they contain. Gravitational wave detectors like LIGO and Virgo capture merger signatures, offering clues about their internal structure. Neutron stars challenge our understanding, revealing the limits of our theories and pointing toward new mysteries. They show us what the universe does under maximum pressure and what's hiding inside objects that aren't black holes. They are possibilities, whispers from the edge of known physics. The enduring legacy: why neutron stars matter. Neutron stars may seem like cosmic loners, but they play an outsized role in the universe. Natural laboratories. We can't build anything like them on Earth. They show us what happens when matter is pushed to the absolute edge of existence, essentially running physics experiments on an unattainable scale. Testing gravity. They test Einstein's general theory of relativity more severely than anywhere else. When two neutron stars orbit and collide, their gravitational wave emission gives us incredibly detailed data on how gravity works in the strongest fields. The Hulse-Taylor binary pulsar provided the earliest and most famous indirect confirmation of gravitational wave theory years before direct detection. Exploring matter. They help us understand the nature of matter itself, what happens when neutrons compress, what superfluid interiors look like, and the strength of nuclear matter in an entire star. Their structure and behavior provide clues to the equation of state, narrowing down possibilities for exotic matter like quark matter or strange matter. Element creation. When they merge, they create the universe's heavy elements like gold, platinum, and uranium, which don't form in ordinary stars. Neutron star mergers answered the question of where these heaviest elements come from. Cosmic clocks, pulsars spin with incredible regularity, making them useful for keeping time. Some millisecond pulsars are accurate to within a few billionths of a second, potentially serving as a cosmic GPS system for future spacecraft. Multi-messenger astronomy. Neutron stars are perfect sources for the new era of science that combines observations from light, gravitational waves, neutrinos, and other particles. They flash in radio waves, explode in visible light, and vibrate spacetime when they collide, helping us build a complete picture of the cosmos. Beyond science, neutron stars hold a poetic role. They are reminders of the universe's recycling. A massive star dies not into nothingness, but into something new, a neutron star. This new star may merge, creating a kilonova, spreading elements that seed future stars, planets, and perhaps even life. They are not just remnants of destruction, but seeds for new beginnings, showing that even the densest, most extreme objects have a place in the cosmic story. Imagining the visit, a thought experiment. What if we could visit a neutron star? In reality, you'd be crushed and vaporized instantly, but in a thought experiment, safe in a perfectly engineered pod. As your ship approaches, you'd be struck by its small Cisano bigger than a city, around 20 kilometers across, yet holding the mass of hundreds of thousands of Earths. There's no atmosphere in the usual sense, just a smooth, rigid, unimaginably dense outer shell of compressed atomic nuclei like brushed metal. The light you see, converted from X-rays, would bathe the star in ghostly blues and whites. Even hundreds of kilometers away, the star's immense gravity pulls hard. Without artificial gravity, you'd fall at unimaginable speeds. The escape velocity is around 150 kilometers, more than half the speed of light. Dropping a coin from 1 meter would hit the surface in less than a microsecond, releasing bomb-like energy. As you drift closer, the horizon curves upward due to gravitational lensing, allowing you to see more than half the surface at once. Your onboard clock ticks differently due to gravitational time dilation. Every second passes more slowly for you than on Earth. An hour in orbit could mean several hours or days back home. The neutron star below rotates. If it's a fast pulsar, the surface whirls like a record player, flickering with radiation beams. The magnetic field is intense, trillions, even quadrillions of times stronger than Earth's, strong enough to distort atoms and flicker your ship's electronics. Peering beneath the crust, your imaginary probe would pass through. A few centimeter-thick plasma atmosphere. A solid outer crust of tightly packed nuclei. An inner crust where electrons merge with protons to form neutrons that drip out. The bizarre nuclear pasta layer where matter forms spaghetti or lasagna-like shapes. The superfluid core of neutrons flowing without resistance. And at the very center, perhaps a core of quark matter or something even stranger. On the surface, it's eerily calm. No sounds in space, but the silence would feel louder, like immense compression. Occasionally, the star might glitch, a sudden spin-up, a tiny hiccup in its perfect rhythm, instantly picked up by instruments. You pull away, the star shrinking to a speck, still pulsing, still whispering. Your clocks resynchronize with Earth time. You've seen a place where physics is stretched to its limits, where matter folds in on itself, where gravity sculpts and time flows like syrup. You've looked into the eye of a collapsed sun and returned, changed. Just imagining such a place is enough to shift your perspective, making the universe feel bigger, reminding you that even in its smallest, darkest corners, wonder awaits. A cosmic symbol. Neutron stars in imagination. Neutron stars have captured more than just scientists' attention. They've rooted themselves in the human imagination. They are paradoxes, dead stars that still pulse, corpses that glow, remnants that spin with perfect timing as if the universe couldn't fully let go. In science fiction, they are often hazards, sources of mystery, or even gateways to other dimensions. Writers imagine civilizations living on or around them, perhaps machine or energy-based life. Arthur C. Clarke's Neutron Tide famously illustrates their danger with a star-mangled spanner punchline. Beyond fiction, they appear in poetry, art, and philosophy, symbolizing permanence, transformation, or quiet persistence after destruction. The idea of a star collapsing into something unimaginably dense, spinning for billions of years, is deeply human. In popular culture, they show up in Star Trek, Doctor Who, The Expanse, and video games as dangerous obstacles. The real-world wonder is undeniable. A 20-kilometer-wide object spinning hundreds of times per second and weighing more than the Suna contrast that feels like poetry written in physics. People create art and music inspired by pulsar rhythms. Actual recordings of pulsar data are like a cosmic heartbeat, steady and alien. One of the most touching stories involves the Voyager missions of 1977. On the golden record carried by each spacecraft, a diagram uses pulsars as reference points, each with its unique timing signal, like a cosmic fingerprint. This serves as Earth's return address on a message thrown into the cosmic sea, showing how we view these stars. Reliable, predictable, useful, beautiful, and a little mysterious. Despite our observations and models, neutron stars remain puzzles what's inside them. How do their magnetic fields evolve? They challenge our understanding, asking questions through their very existence about death and transformation, time and pressure, and what remains when everything else falls away. A neutron star is a riddle written in mass and magnetism, and like all good riddles, it's enough just to know it's out there, pulsing, waiting, reminding us the universe is full of stranger things than we've ever imagined. The final question: what remains? So, what happens after a star explodes? We've journeyed far. We've seen massive stars burn, collapse into impossible density, warp time and space, and pulse like cosmic metronomes. We've watched them hiccup, flare, crack, and collide, following their light and gravitational whispers across millions of light years. What remains is not an ending. A neutron star isn't just what's left after destruction, it's what emerges from it. A transformation, not a disappearance. A rhythm, not a silence. A question, not a conclusion. Even after all the science, theories, and observations, these little stars still ask big questions. What is matter when crushed beyond recognition? What does gravity do at its absolute limit? What strange physics hides beneath that crust? Are we seeing the final state of matter or just the beginning of something stranger? Perhaps the answer is both. Neutron stars show us that even when something ends, something else begins. There's elegance in collapse, beauty in extremity, and a kind of peace in the spinning heartbeat of a dead star. As you drift off tonight, I hope you carry this quiet reminder. The universe is vast, full of endings, full of beginnings, and always, always asking the next question. Sleep well.